Hello, my name is Yunhai Han and I am a researcher in the Laboratory for Intelligent Decision and Autonomous Robots at Georgia Tech. I am here to present our work on learning a generalizable robotic grasping framework using both visual and tactile sensors via transformers. The motivations for our works can be summarized as 3 points. First, up to now, robots still have some difficulty in handling the grasping tasks where the grasped object's contact parameters are prone to vary. For example, for the fruit grasping, different fruits share various hardness and surface texture, so the deformation captured by sensor during grasping process would vary, which makes it hard to find a generalizable grasping strategy for different fruits. We show an example below in the picture, where the robot arm is expected to place the orange into the target basket. The robot needs to first figure out what is the appropriate grasping force for the safe grasping and then gets to know it is an orange in order to put it into the correct basket. What's more, as we all know, among the other fruits, apples are harder than oranges and tomatoes have more slippery surfaces. Therefore, how to enable the robot to safely grasp each fruit without any prior knowledge would be challenging. The second motivation is that tactile sensing technology is getting popular because it is able to provide dense contact information. So, we would like to explore how the gel-site tactile data can benefit the robotic grasping tasks, integrated with camera visual data. Third, in this work, we employ a state-of-the-art deep learning models, transformer model, for processing the sensor image data. This type of model was originally proposed for the natural language processing tasks and it has been gradually getting the attention from the computer vision community since late 2020. The transformer models have several advantages over the traditional models and they are more adaptable to complex tasks. Several recent published works have shown that they can achieve new best results for various image learning tasks using transformers. Thus, we believe it is worth adopting the transformer models for robotic grasping tasks, where more dynamical interactions are involved compared with common image learning tasks. Here, we show the transformer-based grasping framework. There are 5 main components: input data, transformer, fusion models, prediction model and inference. The input data are the visual and tactile sensor recordings when the gripper performs 2 predefined explorative actions, pinching and sliding, before the actual grasping. The aim of designing these actions is to let the robot obtain the physical information of the fruits. The transformer models then process these image sequences and output a vector with size d for each sensor modality and for each actions. The fusion models take these vectors from transformer models and project it to a low-dimensional space as a fused physical feature embedding. The prediction model takes this embedding and a grasping threshold candidate as inputs and outputs the upcoming grasping outcome. Finally, the control policy is formulated via inference, which means we can either uniformly or randomly sample the thresholds and feed each of them into the prediction model and select the one that predicts a safe grasping. This process is shown in the top right black box. All the codes are made public and the link is included in the paper. For the data collection, we perform the fruit grasping with various grasping force thresholds on different fruits to train and test the models. The first thing we have to mention is the control parameter used in this work. Since gel-site is a vision-based tactile sensor, so we employ the maximum depth value of the tactile images as the approximation of grasping forces. If the maximum depth value feedback is larger than the selected threshold for 3 continuous steps, the gripper will begin to grasp the fruit. Hence, by choosing different thresholds, the robot would grasp the fruits with different grasping strength. Also, note that the unit of these thresholds is pixel, which is omitted for the purpose of readability. Now, using orange as an example, we show 3 typical cases for each label, which are slip, safe grasping and potential damage. The robot first performs the 2 explorative actions on the orange, and then we manually set the force threshold and execute the grasping. For case 1, the threshold is set to be 4 and the figure at bottom shows the maximum depth value feedback during the grasping. The grasping result for case 1 is slip and these data and the grasping label will be used for the network training. For case 2, the threshold is set to be 6 and it leads to a safe grasping. For case 3, the threshold is set to be 9, which is a little large because from the figure, you can see that the maximum depth value cannot reach the threshold due to the orange's deformation. If the gripper continues to apply this grasping strength, it may cause the potential damage to the orange or even the gripper hardware, which we definitely want to avoid for the purpose of safe grasping. The other fruit examples can be found on the project GitHub. During training, we in total used 5 fruits and they are orange, apple, tomato, plum and lemon. Also, the whole dataset is available online and the link can be found from the GitHub webpage as well. The trained frameworks are then deployed online on the robot manipulator to estimate the safe grasping force for both seen and unseen fruits. For the online deployment, the robot would first perform the 2 explorative actions as we did for the data collection, to collect the input data and obtain the physical knowledge of each target fruit. Through inference, the robot is able to pick up the grasping force threshold for safe grasping. As shown in all the examples, the framework performs well on both seen and unseen fruits. We did 50 grasping for each fruit and the statistics results can be found in the paper. We also test the fruit classification model on the seen fruits during online deployments, which enables the robot to place each fruit into separate bins. The fruit classification model uses another MLP network which takes the fused physical feature embedding as input and outputs the labels of the grasped fruit type. In the left image, we put 5 different fruits on the table, of which the positions are known to the robot. Then, as shown in the right video, the robot would pick up each fruit safely using the proposed framework and put each of them into the target bin. The grasping procedures are the same as demonstrated in the last slide. In addition to our own dataset, we test the transformer models on a public dataset for slip detection and they outperform the traditional CNN plus LSTM methods. The results can also be found in our paper. We now visualize the attention to understand what the transformer models learned from the grasping training dataset. For the temporal attention shown in the right, we show the temporal attention from selected image patches at the final frame to their temporally preceding neighbors. From top to bottom rows, the images are collected from tactile pinching, tactile sliding, visual pinching and visual sliding, respectively. Each image is split into 10 × 10 patches, among which several patches are selected and denoted within the dashed ellipsoid in final frame. The brighter the patch color is, the more attention is paid to the patch from its temporal neighbor at final frame. It can be seen that the image patches in the final frame do not only attend to themselves, but also their temporal neighbors in preceding frames. In addition, in right bottom figure, we show the normalized temporal attention weights of all selected image patches. An intriguing observation is that the image patches in first 2 frames, when the gripper initially touched the objects, share larger attention weights compared with succeeding intermediate frames. Our conjecture of this observation is that the initial and ending contact information is more inferable to the physical status of the grasped objects, as well as to the grasping outcome. To sum up, compared with recurrent networks which have trouble of keeping the information of the previous inputs, the transformer models are able to mitigate this problem because of the different model architecture. For the spatial attention shown in the left, we can see that for tactile images, the model mostly attends to the local contact region, and for visual images, the model attends to the fruit surface near gripper's fingertips. Therefore, the transformer models can incorporate more contact information for the grasping task. Besides, it should be noted that the interpretability of attention mechanisms may provide with an alternative way of analyzing how deep learning methods understand the object's physical deformation properties captured by tactile and visual sensors during robotic contact-rich tasks. Thank you for watching.